This video is for Math 1325, and we're working on section 3.1, and this will be the first actual taste of calculus concepts. The first major concept in calculus is called a limit, and there are a number of ways to do a limit. The beginning of this will be mostly looking at graphs or tables, but then there's also some algebra techniques you can do as well to solve for them. The idea of a limit is, say you have some kind of graph. A good example of it is like a piecewise function where maybe the graph comes in like this, there's an open circle there, and then it keeps going. And maybe you just have a graph like that with a hole in the graph. And if this, say this is x equals 3 right here, the function evaluated at 3 is undefined because there's literally nothing there at 3 to touch. So many times in math, when things go unanswered, at some point somebody comes up with a way to come up with an answer. So the idea of a limit is I can do limit, which is abbreviated LIM, and then you put x approaches 3 with a little arrow of the function. And this can have an answer or not, completely independent of whether the function had an answer or not. But just this is an example here where the function didn't have an answer, it was undefined, but maybe there's in essence what the answer would have been. So think of it this way, as like, what if that hole wasn't there? And let's say that this is -1, -2 right here for the y. Well, somebody was looking at this in the past and said, well, if only there wasn't a hole right here, f of 3 would have equaled -2 otherwise. But because there is a hole there, it's technically undefined, but in essence, the graph is getting really close to -2. So the limit can have an answer of -2 even if the function is undefined at that spot. That's kind of where this was born from. So really, to do that though, the reason why the answer is -2 here is if you're going to do a limit, you want to actually look at, and this is what the first problem is doing, you want to look at what are called one-sided limits first. So the way this is written is you put 3 with a little negative sign. This means from the left. The negative means from the left. And then you do another one from the right with a little plus there. So the idea is I'm coming in from the left and getting as close to 3 as possible without actually reaching 3. So I'd want to get to like 2.99999. And then this circle here is kind of exaggeratedly big. It doesn't actually take up any space, but just for us humans, we put a big circle there to let the human eye see that better. But really this hole would be so tiny the human eye wouldn't even see it. And if you got really close to 3 from the left, you would get really close to -2, but just slightly above -2. Kind of like where the top of that circle is taking you to, the y value. So that's, it can get arbitrarily close actually. So we would say that that's close enough to -2 to just say it's -2. Because it could be -1.99999, really close to -2. And then when you come in from the right, a similar deal, you get really close to 3 from the right, 3.00001. That's going to take you down to this lower part of the circle, which again, the circle's bigger than it really would be. So that just means you're slightly below -2, like -2.0001. So if both of these answers get really close to the same value, even if one's like -1.999 and the other one's -2.0001, that's close enough to say they agree with each other. These two have to agree with each other in order to have an overall limit, which is really what we're mostly trying to answer. Some problems will actually ask for the left-sided limit first, the right-sided limit second, and then the overall limit. And then they might even ask for the function value, which could have a same answer, a different answer, or no answer at all. But sometimes they just ask for the limit without doing the left and right-sided. They don't have answers for them, but it's always good to think of that first. If these two disagree with each other, fully disagree, not just a little bit off, but if they fully disagree, if they're completely different answers, then there is no limit. And that's what this first problem is saying, is if the limit as x approaches 2 from the left, if that happens to equal 4, if you're really close to 4 of the y value, but then you do it again a little bit to the right of 2, limit from the right. If that answer is 9, then what is the overall limit answer? The answer is it does not exist, which is similar to saying undefined. And that's kind of the way, that's usually the rule, is when the function doesn't have an answer, you say undefined. If a limit doesn't have an answer, we say does not exist. A good example of this situation is often these will come from piecewise functions where you have different parts of the graph going on. A real basic piecewise function is, what was the x value? 2. When x is 2, you might have a closed circle here at 2 going this way. And that was 9. That's a y value of 9. And then at a y value of 4, there might be an open circle going that way. Whether they're horizontal or even diagonal doesn't really matter, but the point is, if I come close to 2 from the left, I'm going to be right there at 4. But when I come in close to 2 from the right, then I'm up here at 9. So the left-sided limit is 4, the right-sided limit is 9. They disagree with each other, so automatically the overall limit does not exist. Limit as x approaches 2 overall does not exist. This is kind of the opposite scenario of the one I was talking about at the beginning, because f of 2 exactly, unlike my previous problem that was undefined, here f of 2 actually equals 9. Actually, the function has an answer and the limit doesn't. That can happen because there's literally a closed circle at 9. Now, these could have both been open circles. That's always a potential. So there could be a limit does not exist, and the function could be undefined at exactly the same time. Sometimes they both have an answer. Sometimes they both have an answer that agrees with each other, or both have an answer that disagrees with each other. Sometimes one of these two has an answer and the other doesn't, and sometimes they both don't have answers. You're really doing limits independently of function answers. Just because one has an answer doesn't really affect what the answer of the other one's going to be. And we don't really care if, at this point we're learning limits, we don't care if the function has an answer or not, but that will come into play later. So here they're not even talking about the function value. On the first problem, it had nothing to do with what was f of 2. That wasn't even part of this problem at all. So the first idea is, if your two one-sided limits disagree with each other, then definitely the answer is there is no limit answer. It does not exist. So what if the left-sided limit is 2, the right-sided limit is 2, and f of 8 equals negative 2? What can you say about the overall limit as x approaches 8? This here has no effect on the answer, so they're just trying to trick you by telling you that. This could have been negative 2 or positive 2 or undefined or anything else. It's not going to affect this limit answer. This limit answer completely comes from the two one-sided limits. If they disagree, the answer automatically does not exist. If they agree, that's what its answer is, automatically. So once these two were both 2's, this is always going to be a 2 regardless of what the function's doing. It doesn't matter if the function is different or agrees with it or is undefined. Any of that could have happened. Okay, so here's more limits from a graph. And there's 2 parts here, but I would also include 3 parts to each of these 2 parts. So if you really want to do the limit as x approaches negative 3 of the function f of x, which is this kind of squiggly graph, and it's a piecewise graph because we have holes in the graph, 2 pieces broken apart from each other, and then you can put an arbitrary closed circle wherever you want. But regardless of what's happening in a function or in a graph, if you really want to do this, you should actually, even though they don't have it, you should be thinking of these at least separately in your mind or on your scratch paper. The first part wants x to be close to -3. So you should be thinking from the left first. What's the answer from the left? What's the answer from the right? Even though they sometimes ask for these, but often they don't. And when they don't, you should still be thinking about them yourself, though, before you try to answer the actual part A question of what's the limit as x approaches -3. So until you get to the algebra technique problems, you really can't do a limit directly on its own. You really need to be thinking about the left and the right side of limits. If you're doing the graphing method or what's called the table method, you really need to see these two answers. We need to see if these two answers agree or disagree with each other. So get close to -3, come from the left side. There's -6, -5, -4, here's -3. There's actually an answer exactly at -3, but that doesn't matter for limits. So move slightly to the left of that spot. And you're going to go up or down until you touch the graph. And it can't be both, because then it wouldn't be a function. It would violate the vertical line test. But sometimes you have to go up, sometimes you have to go down. If I go down, there's nothing to touch down here. But if I go up, I would touch right there, right this little curve coming out of the circle. And again, the circle is exaggeratingly big. It doesn't have to really be that big. So that curvy part would come right to where this X is forming, where the graph paper is crisscrossing itself, right where the circle literally is. You can get arbitrarily close to that circle, and you'll see this when we get to the table method. So just think about being as close to that circle as possible, and then you go across till you touch the y-axis. You would actually be touching it slightly above 2, but it's close enough to say 2. The left-sided limit is 2. Then I come in from the right-hand side until I get close to -3, as close as possible without touching it. Again, I would have to go up until I touch the graph, and then I would be slightly below the circle. So now the answer is like 1.9999, but that's still close enough to 2. So that left-sided limit was 2. The right-sided limit matches it 2. We have agreement here. When these agree, the answer is 2 for this, even though f of -3 had a different answer. And this f of -3 doesn't affect this, so you don't have to do this yet. But I'm just going to note it because we are going to do it in section 3.2. This actually equals 0, but it doesn't affect this answer here. It didn't matter if this was 0 or 2 or -2 or even undefined. This was going to still be 2 because these two agree with each other. But it actually is, there is a y value of 0 exactly at -3, even though that doesn't matter here. So the limit for -3 is 2. Then if I repeat this at -1, which is right here where this open circle is, so now you want to do all three of these all over again. Limit as x approaches -1 from the left first. Get an answer for this. Then do it again from the right. And get an answer for that. And then if you hope to have an overall answer, these two have to agree with each other. If these two disagree, then there's no answer to the actual question they're asking for, which is the overall limit of -1, which may or may not be anything similar to what f of -1 is. So come in from the left, get as close to -1 as possible. You'd be right on the left of this open circle. If you go up, there's nothing to touch. But if you go down, you're going to touch right there coming out of this closed circle. So then once you see where you're at, move over to the y-axis. And I'm a little bit above this spot, but you can get really close to it. So you're a little bit above -1. That's close enough to say -1. The left-sided limit's -1. Then I get from the right, I'm coming in from the right all the way till I get close to -1 of the x-axis. I would be right here on the right-hand side of that open circle. If I go down, I don't touch anything. You'd just fly right by that. But you go up, you'd touch right away. So you're just slightly above 0. So that's close enough to say 0. But these two disagree with each other. Disagree, we have disagreement between the left and the right side of the limit, so that automatically means the overall limit does not exist. Even though, and this has nothing to do with this problem, but it will later, f of -1 has an answer actually. I'm going to go ahead and do it because you're going to need it later, but if you're exactly at -1 where this hole is, there's actually a closed circle down here at -1. So in algebra, they would do f of -1 in algebra, and they would say the answer is -1. And these can agree or disagree, or one can have an answer and one might not, or they both might not have an answer. So that these are independent answers though. And we don't really need this one to do the problem, but I'm just pointing it out for now. So the limit at -1 does not exist, even though the limit at -3 did. Okay, same problem. See, now they actually are asking for the left and the right side of the limit. You really should do that every time, whether they ask for it or not. So they want you to do all 4 things I've been doing. They want the left-sided limit, the right-sided limit, the overall limit, and then the f of answer, the function answer. I always do all 4 of these every time I get a new one. So when you're close to a equals 0, when you're right on the y-axis, there may or may not be an exact answer there. There actually is an exact answer there, but that doesn't matter for limits. So I want to come in from the left until I get really, really close to 0, which would be right where that circle is. The only point I can touch vertically from there is going up, but you wouldn't go up very far. You're right there. So the left-sided limit is 0, at 0. Then I come in from the right till I get close to x equals 0, which would be the right-hand side of this circle. Now if I go up, I don't touch anything. But if I go down, I would only touch right there where that arrow's coming out of that circle. So I'm virtually at -2 right there. So the right-sided limit, where the plus is, that's -2. The left-sided limit was 0. The right-sided limit was -2. They disagree with each other. So automatically the overall limit does not exist. But that has no effect on the final part here. F of 0 has an exact answer of -1 because there's a closed circle right at -1. So this is what can happen where everything disagreed really. There was, out of all 4 of those, none of them agreed with each other. We had an answer of 0, then -2, then no answer, and then -1. All 4 of those were different from each other. Sometimes all 4 of them are exactly the same. That can happen. In fact, it's going to happen here next with 2, and that's why they have 2 parts here. When a is 2, if you get really close to 2 on the left, like 1.9999, you would go down, and then you would hit the graph right there, slightly below -1. But close enough to -1 to say that that's -1. So coming in from the left, getting close to 2, you're slightly below -1. But when you come in from the right, close to 2, like 2.001, you would have to again go down, and you would touch slightly above -1, but again, really close to -1. So that would also be -1. Since those 2 answers agreed with each other, -1 and -1, then this answer is automatically -1. And exactly at 2, the graph is exactly at -1. The line literally crosses right through -1 when x is 2. So all 4 of those answers agreed with each other. This is a very good example where one set of the 4 answers, all 4 of them were different from each other. And then for a second set on the exact same graph, all 4 of these answers agreed with each other. So that's why you really can't, there's really no shortcuts here when you're doing this graphing method. You really got to go through all 4 parts on even if they don't ask for all 4 of them. Okay, now we have a separate concept. This is mostly the same, but the issue different here is right there. You can also do a limit out to an infinity, like out to negative infinity or out to positive infinity. These are called limits at infinity. And really, we kind of deal with them in college algebra too. In fact, that's kind of what a horizontal asymptote is about. A horizontal asymptote is where does the graph level off at as you go way out to either infinity or negative infinity. So if it levels off like this graph out at positive infinity, then the limit as x approaches positive infinity would actually be whatever this horizontal asymptote is, which I guess is 2.75. But if you go way out to negative infinity, this graph's mostly going downward. So that just means it's going to continue downward forever. So as you went way off to the left, it's just going to keep going down and down and down and down. And so therefore, the limit doesn't really exist, but there's a couple of reasons why a limit doesn't exist. The main way is when the left and right set of limits disagree with each other. But if a limit actually goes to some infinity or negative infinity value, then we can say that to be a little more specific. So we can say that that limit is negative infinity, even though technically that's not an actual answer to anything. So what they do to be specific here is if you get infinity or negative infinity, you put that in there, even though technically that still kind of means there is no limit. And then they have a higher level of that by saying the limit does not exist and it's not infinity or negative infinity. That happens when you have disagreement on the left and right side. So just to distinguish that, but technically if you're saying the limit answer is negative infinity or positive infinity, you're technically saying it doesn't exist either because infinity means it goes on forever. But if it doesn't exist because it's going on forever towards infinity or negative infinity, then we can distinguish that answer from just saying it doesn't exist. So that problem number 5, this would have had a different answer if they would have done positive infinity. And I'm not really doing left and right-sided limits here because you can't get to infinity is the problem. You have to have a specific number here to do a left of it and a right of it. You can't get to infinity, so there's no way to go a little bit to the left and a little bit to the right of it. So if you're going out to infinity, one way is to look at a graph and just see, is it going, most graphs way out to the left or right are either going to shoot straight down or go straight up, or they level off somewhere. So this one, if this was positive infinity, it levels off at 2.75. That would have been the answer then. Okay, this is called the table method. And this works all the time, but unfortunately it can be tedious, especially if you don't have a good calculator. But without a calculator, a graphing calculator, you just got to plug 4.9 in, get your answer. Then you plug 4.99 in, get your answer, and it gets a little boring after a while. But if you do have a graphing calculator, I don't know how well you can see this, but let me try turning a light on and see if that helps. Be a little better when the light shines there. Okay, so I'm going to press my y equals button right here in the top left. And notice I already have some kind of equation in there. So I'm going to clear it out. And because I have a fraction, fractions have implied parentheses, even though they don't put them. So I'm going to put parenthesis. I'll type it so you can see what I'm typing and then zoom in on it. Parenthesis x. X is right next to the alpha key. X raised, the exponent button's right above division, raised to the third power, minus 125, close parenthesis. So there's the top of the fraction, divided by parenthesis x minus 5, close parenthesis. So I've put the entire function into my y1 of my graphing calculator. Then you want to press second window to get to what's called table setup. And if you set them both to automatic, or both of them, no, if they're both set to automatic, which is usually the case in algebra, then you have to put numbers into these two slots. But if you leave independent on ask, then these two numbers up here don't matter. And that's what I'm doing is I have the independent as ask, And then it'll ask me what I want to put in, and I'll just be able to put these 6 numbers in. And then the dependence on automatic, that means the answer will automatically calculate. So you just have to one time go to second window and change your independent to ask, and that's all you have to do in this window. And once you do, you'll never have to come back here again. We want to get to the table. The table's right above the graph button, so second graph gets you to the table. Now I have stuff in here from a previous problem, so you just hit delete to get rid of the old stuff. Delete, 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 delete. I just cleared it out. So first I'm going to type in 4.9. This is where it's asking me what x do I want. So 4.9. When I press enter, it'll automatically calculate the y answer. And then you can up arrow and right arrow to get right on top of it, because when you look at it up here, it's kind of rounded, but down at the bottom, if it's a long decimal, it'll show you the whole thing at the bottom. So here it's not rounded, but it's 73.51. So this can help speed up all these calculations, because otherwise this method can take a long time actually. If you just have a plain calculator that adds, subtracts, multiplies, and divides, you might be spending 20 minutes on one problem. So here it goes real quick. Now you can either delete that, or I like to leave it in until I'm all done. So I'll just leave that one there. And now I'm going to put 4.99. And then again, you might have to go up and over to see if there's a longer decimal at the bottom, because they'll say where to round to. This says round to 3 decimals. So I just got 74.8501. So I'll just leave that 850 in the decimal part. And now we're going to put 4.999 in. So go back down and to the left, 4.999. And now go up and to the right so you can see what it says. 74.985001. So that's just 74.985. This is the idea of coming in from the left. I'm getting closer and closer to 5. I'm trying to find the limit at 5. These 3 values right here, this is like the left-sided limit in a graph. I'm getting closer and closer to 5 from the left. I'm first at 4.9, then 4.99, then 4.999. And look what's happening to the y value. First it was 73.5, then it was 74.8, now it's 74.98. So you could even add your own and put 4.999999 and put a whole bunch of 9s if you wanted to. And then it virtually says the answer is 75. In fact, it rounds it to 75 because it's so close to that. But really what it should have been is 74.9999999. Just the calculator ran out of memory after a while. But see, that shows you that you're getting closer and closer and closer to 75. So this box right here is telling me that the left-sided limit is 75. So when I come in from the right, if this one also becomes 75, close to it, then I can say the overall limit is 75. But if this gets in closer and closer to some other value besides 75, then the limit won't exist. And if you just go out to this one, you can tell the answer, but they won't let you get away with that. So you got to type all these in anyway. So let me put 5.1 next. That one came out to exactly 76.51, which is not really extremely close to 75 yet. But then if I do another one for 5.01, now it's 75.150. And then I need to do 5.001. Whoops, I gotta go down and over. 5.001. That one is 75.015001. So see how the left-sided limit is a little less than 75. The right-sided limit is a little more than 75, but they're both extremely close to 75. And in fact, if I put more 9s or more 0s in each one of these, then I can get as arbitrarily close to 75 as I want. So that's why it's okay if you're not exactly at 75. You can just, as long as you can tell what you're getting closer and closer to. Both of these are getting closer and closer to 75. So after you show that you did the table method correctly, then you can find the answer that this is 75. If those two answers would have disagreed with each other, if there would have been disagreement here and here, Notice that part B said the limit does not exist and it's not infinity or negative infinity. Because technically, if it is infinity or negative infinity, then it doesn't exist either. But they consider that a less specific answer, I guess, than this. So the way you would say that, only the part B only happens when there's disagreement on the left and right sided limits. If it's a case where they just go to infinity, you can have agreement. The left sided limit can be like 99999, and then the right sided limit can be 99999, and they can both be going towards infinity. So technically they're agreeing with each other that they're going close to infinity. So then we would be a little more specific and say that the limit is infinity, even though technically that doesn't exist either. Okay, then we do what's called properties of limits, and it turns out these are really nice and easy to do. That if you know the answer to a limit for one function at a given value like 6, the limit as x approaches 6 of a first function equals 8. And then if I do the limit as x approaches 6 for a different function, g of x, and if that equals 40, if you know the individual answers, then it turns out that if you multiply by a constant or you do some kind of simple math like adding, subtracting, multiplying, or dividing, you can just take the answers and do that to the answers. So in other words, if I want the limit as x approaches 6 of f of x divided by g of x, I already know the limits individually, so I can take their individual answers and just do what the math is saying. I can just divide them. Literally 8 divided by 40 would be the answer. Unless here it says type in integer or a simplified fraction, but in theory, the answer would be 8 over 40, but that does reduce by 8, so we do need to reduce it to 1/5 or they're going to count it wrong because they asked for a simplified fraction. But really what it is 8 divided by 40. Or if they could have said, what's the limit as x approaches 6 for f of x plus g of x? Then you would do 8 plus 40. So that's what's real nice is limits can be done individually or together. So same deal here. I can add 2 and I can divide by a constant times one of them. So since the limit as x approaches 7 for f of x, they tell me that that answer is 8. They already took the time to figure it out separately. There's no way for you to figure it out because they'd have to give you a graph or a function, so they're purposely not giving you that. But they're telling you the limit for f of x is 8, the limit for g of x is 6, so you can just put the 8 in here and you can just put the 6 there, and you can put another 6 where that g of x is. So you're literally going to get 8 plus 6, the top's 14, and the bottom is 4 times 6, which is 24. 14 over 24 is literally what you get just by plugging the 8 and the 6 in. And then again, simplified fraction, those divide by 2. So make that a 12 and make this a 7. So a limit of a sum is the same thing as the sum of the limits. That's what we're saying here. The order doesn't matter if you have things like that. Okay, here's also some algebra techniques you can do. So one rule that you'll learn soon, if not right now, is that if you ever want to do the limit of a rational function, it turns out that the limit of a rational function will equal the same as the function evaluated at that number unless the answer is undefined. So I have a rational function, which is a fancy way to say fraction with polynomials in each part. Normally, the limit at 10 may or may not equal f of 10. Those are normally independent calculations. They can agree or they can disagree, and knowing one doesn't automatically tell you the other. But if you ever have polynomials are a special case. Polynomials, the limit of a polynomial always equals the function value of a polynomial when you're doing the same value. So limit as x approaches 10 will always equal f of 10 in any kind of polynomial. But if you don't have a polynomial like these here, these are not polynomials here, that rule doesn't apply to most cases. So polynomials are special cases. And then because a rational function is two polynomials divided by each other, it works here too, unless you get an undefined answer. So the first thing you try on a rational function is you just try to do f of 10. If I plug 10 in, would I get some kind of answer? If you get an answer, that's always going to be the limit answer if you have a polynomial or a rational function. But here you're literally going to get 0 divided by 0, which is undefined. So you try that first. It didn't work. Sometimes it will if you have a rational function. And if you have a polynomial, it'll always work. So if it doesn't work, then here's some other techniques we can do. Factoring is very helpful on many of these rational functions. So if you notice that the top of the fraction factored into difference of squares, x plus 10 times x minus 10. And the denominator is x minus 10. Those cancel. And after I cancel them, what's left is literally a polynomial. So now this was technically f of x here. So I've created a new function, but the limit as x approaches 10 for a different function that comes from simplifying a given function, if that creates a situation where you can get the answer from it, then those two limits will always agree with each other. So now I can suddenly do g of 10 because it won't be undefined anymore. It'll just be plugging 10 into a polynomial. So now you can just plug the 10 in. 10 plus 10 is 20. So it's a technique in order to find the limit of a rational function. You're actually doing it from a simplified version of the rational function. And even though that creates a different function answer, the original function answer was undefined, and the new function answer is 20. Those don't really seem to agree with each other. That's okay. In limits, they still will agree with each other. And in fact, in college algebra, they're taught how to graph a problem like this. What ends up happening is when you can factor and cancel, this is where you lose your vertical asymptote. You would have had a vertical asymptote at 10, but you lost it because it canceled with the numerator. So then x plus 10 is just linear. That's all that's left literally is y equals x plus 10. That's a line, and it'll have a hole in it at 10. So what will happen is when x is 10, the y-intercept was 10, and the slope was up 1 over 1, up 1 over 1. If you keep doing that, when you get to 10, there'll be a hole in the graph. But it's a line with a hole in the graph, literally, is what that original function is. F of x is a line with a hole in the graph. So that's why f of 10 is undefined. F of 10 is undefined because there's nothing there but a hole. But if you go a little bit to the left of 10, 9.99999, you're going to be slightly below a y value here. And then a little to the right of 10, you're going to be slightly above that same y value. And in fact, because the slope was 1, every time you go up 1 over 1, up 1 over 1, if you do that 10 times, this y value is going to turn out to be 20 where that's happening. So even the graphing method can confirm this answer. But the point of problems like 9 is we want to get these answers quicker than a graph or a table method. The graphing method and the table method always work, but they can often take a lot longer to do than algebra techniques that or properties of limits that help us get the answer faster. So I can know this answer is 20 just by factoring and canceling and plugging the 10 in. It goes much quicker than the graphing method or the table method, but those would have worked. I could have redone the table method on this the same way I did that other one, and the answer would have been 20. But if you're looking for less work, especially if you don't have a graphing calculator, this can help on some of these. So number 10, limit as x approaches 8. And notice I won't be able to plug 8 in because the denominator is x minus 8. So that's either a hole in the graph or that's a vertical asymptote. Either way, I can't plug 8 in. So x squared minus 3x minus 40. If I can factor and cancel it out, not only will it no longer be a vertical asymptote, it'll just be a hole in the graph. But then I'll be able to get the limit answer too. If I can't factor and cancel it, then the limit might not exist actually. So luckily this numerator does factor, and you don't have to think too hard. Really just check if x, does it factor into x minus 8 and something else. That's all we really would, that would really help us right here. If I can get something like this. So you can cheat a little bit by knowing the only thing that's going to matter is if it's x minus 8. And there is a negative here, so that means you definitely need one negative and one positive. Multiplying to 40 would have to be 8 times 5 if this one's going to be an 8. Now maybe it's 10 times 4 or 2 times 20. It's possible it might factor some other way. But if it does, it's not going to help me cancel it. So then it won't matter at that point. But luckily this works because there's negative 8x and here's positive 5x. That does add up to negative 3x. Or you could say 5 minus 8 subtracts the negative 3. So it does factor and cancel. So just like problem number 9, I get a simplified version of it that's technically a different function. But it's a reduced version of the original function. So limits of reduced fractions always have the same answer, even though function values don't necessarily have that case. F of 8's undefined, but if I do g of 8, this is when you plug the 8 in, it's like you're doing g of 8. I'm plugging in 8 into a different function. F of 8 was undefined because it made the bottom 0. But g of 8's not undefined. G of 8 is 8 plus 5, which is 13. And therefore, the limit of even the original function will also be 13, because you're just going to have a hole in the graph at that spot. It's going to be a line, the line y equals x plus 5, and there'll be a hole in the graph at h, but other than that, it'll just be going up by a slope of 1. So 13. Okay, here's a good one. Number 11, we got 16 problems, so we got 10 down, 6 to go. The original function has an x minus 64, or was it 8 in the bottom? 64. And you're trying to do the limit as x approaches 64 of the function. Well, in rational functions, the first thing to try is plugging 64 in. If you can plug it into a polynomial or a rational function and get an answer, then that'll always be the limit answer. But it won't work here because the bottom is 0. The top would be 0 too, but if the denominator is 0, the function's undefined. So I tried that first. If they would have given me any other number besides 64, it would have worked too. 64 is the only number that makes the bottom 0. So any other value, the limit I would have got an answer just by plugging 64 in. F of anything besides 64 would have worked. But it is 0, so it's not going to work. You probably remember in algebra a concept called rationalizing the denominator. Well, somebody thought to try this on rationalizing a numerator. When you get a square root of x minus 8, if you multiply by what's called the conjugate is a two-term polynomial or value, a binomial that has the opposite inside sign. There's a minus here, so you need a plus there. And if you do the same thing to the top and bottom of a fraction, then you're not changing the original fraction. It's just a simple equivalent version of it. Because you're doing something divided by itself, which is 1, and anything times 1 is itself. So somebody thought to try this because whenever you multiply conjugates, it always makes radicals go away in algebra. It's one way we get rid of radicals when we don't want them in the bottom. But normally in algebra, we don't do it to the top of the fraction. It's always the bottom and there. But somebody tried this on the top, and watch what happens. Square root of x times square root of x is regular x. Because you have conjugates, the outside and the inside are always opposites and cancel each other. That's the whole point of conjugates. Those two always cancel. And then negative 8 times positive 8 is negative 64. So multiplying conjugates always helps you get rid of radicals. There's never any radicals left after you do that. And somebody who tried that said, wait, they said to themselves, wait a minute, look what happened there. Before they even went to FOIL the bottom out, you don't even have to FOIL the bottom out because there's already a matching factor. I didn't even factor it, and it's like factor and cancel, except I didn't have to do any factoring. So this will cancel that. And the important part here is that we're getting rid of the part that's making the bottom 0. That was what was causing the issue. So just like here, the way the x minus 8 was causing an issue, but I couldn't plug 8 in because the bottom would be 0. By canceling out the bottom, that gets rid of that problem. So you're trying to cancel out this original denominator. That's the way to do it. Now, the numerator can never be blank, so you definitely need to put a 1 here. So what you've done is you've now created an equivalent simplified version of your original problem. It's technically a limit of g of x instead of f of x. But what you have left is 1 over this denominator that has square root of x plus 8. This is a rational function. And because plugging 64 in doesn't make it undefined, then you can just plug 64 in. This is where the limit answer and the function answer agree with each other. In all polynomials, they agree with each other, and in all rational functions, they agree with each other, except at places where the bottom is 0. But this is no longer a place where the bottom is 0, so then I can just plug 64 in. Many times in math and science, issues have been solved by somebody just discovering it by accident. Probably somebody just did this by accident at some point. They just saw this and said, oh, that reminds me in algebra when we multiply by the conjugate to rationalize it. And they tried it here, and it all of a sudden made things a whole lot better. So then you get an answer of 1/16. When originally it seemed like there wasn't going to be an answer. And again, this is kind of what limits are all about. In the original function, f of 64 is undefined, but in the limit of 64, I didn't get an undefined answer. I actually got an answer. Okay, now back to limits at infinity. How do we do limits at infinity if we get something that's maybe too complicated to graph? Because we did one of these earlier where the graph was given to us. So what if our graph just is going to be too long or too hard to do? But I do have a rational function here that helps. 3x squared plus 2x. And then the denominator is 5x squared minus 8x plus 1. Okay, so the trick you do here is whatever the highest degree is for any part of the problem. Here I have a tie for the highest, but it doesn't matter if there's a tie. But say that one of the parts of the fraction had a higher exponent than the other, then that's the one you'd want to go with. But here I have a tie. X squared is the highest degree. So what you do is you take every individual term and you divide by that highest power. And as long as you do the same thing to every part, then that's allowed. I'm technically multiplying, and I'm multiplying the numerator and denominator by 1 over x squared to every single part, distributing it through. And you just need to make sure you pick the highest exponent for this to work. So if you do that, things simplify down. These cancel out. So you're left with a 3 there. This 1x cancels one of these two, but you'd have 2 over x left. These cancel, and you would get a 5. This x would cancel one of those two, and you'd get 8 over x. And this doesn't reduce at all. And now, again, I have a simplified version, or maybe a more complicated version, of my original problem. And I was trying to do limit as x approaches infinity. Well, you could try plugging infinity in, but it's hard to do that because infinity is not a number, it's just a concept. But think about this. What if I have 2 divided by x? What infinity represents is getting larger and larger and larger and larger without bound. So what if I do 2 divided by 10? That's 0.2. But what if I increase it to 2 divided by 100? 0.02. 2 divided by 1,000. 2 divided by 1, 0, 0, 0, 2 divided by a very, very, very large number. That's what going close to infinity means. Then you get 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 2. So infinity means the zeros go on forever and ever and ever here. So then they can go on forever and ever and ever here. So you're getting extremely close to 0, enough to say that that's 0. So if you're going for a limit as x approaches infinity, and if the bottom of a fraction has a larger degree than the top does, that part's going to go to 0. And the limit of a constant is the constant itself. So it doesn't affect constants, but it would make this 2 over x become 0. Wouldn't affect this constant. The 8 over x would go to 0, and the 1 over x squared, even if it's x squared, it really goes to 0 fast. So this is what we did. We intentionally put x's in some of the denominators. Any part with that's going to go to 0 as x approaches infinity. Now, if x wasn't approaching infinity, this technique wouldn't work. If x was approaching 5, you wouldn't want to do this technique, but this works when you're doing limits at infinity. So the final answer is 3 over 5, literally. And in fact, remember that if a rational function has a limit answer, what it really means, at infinity anyway, at infinity, what it really means is that you have a horizontal asymptote that's leveling off of that spot. So another way to do a problem like this is use your algebra knowledge of asymptotes. Remember back in algebra, we said that if the degree of the top and the degree of the bottom are equal to each other in a rational function, the horizontal asymptote is the 2 leading coefficients divided by each other. And we would say the horizontal asymptote is y equals 3/5. That's what this idea is. So even though this is kind of a complicated one to try to graph, and you probably wouldn't know how to do it, it's okay. You got your knowledge of asymptotes. At least you know where the asymptote is, and that's what this is always going to be. If there's a horizontal asymptote in a rational function, that's what the limit at infinity is always going to be. Or you can try the technique of putting in the x squareds into the denominator of every part. So same deal here. Notice that there's an x to the 4th, that's the highest degree. Now maybe you know from college algebra, when the degree in the bottom is bigger, that what kind of a horizontal asymptote you're going to get. If you know that, you already know the answer to this problem. If you don't, then you have to do this. Take each part and put the highest x below each part. So my 9x to the 3rd, notice I am doing limit as x approaches infinity. That's important here. But then my 9x to the 3rd, if I put that over x to the 4th, because that's the highest term, highest degree, plus 9x, put that over x to the 4th, and minus 8, put that one over x to the 4th, and same thing for all 3 denominator parts. 8x to the 4th, and notice I'm only dividing by the x to the 4th. You don't need the 8, you just need the x to the 4th. Minus 8x cubed, put that one over x to the 4th, and then minus 2 over x to the 4th. If every term gets divided by x to the 4th, then you're allowed to do that. And then these 3 will cancel 3 of these 4, but you're still going to have 1x left over in the bottom. So that'll be 9 over x. This 1 will cancel one of those 4. There'll still be 3 left. And this one doesn't even reduce at all. This cancels and leaves just 8. This gets rid of 3 of the 4 x's, but there's still 1 left over. And this doesn't reduce at all. So once I plug infinity in, plugging infinity in is, think of that as just plugging in a very large number like 100 trillion. Anytime there's an x in a denominator, that part goes to 0. So 9 divided by a very large number is close to 0. 9 divided by a very large number cubed is even closer to 0. The higher the exponent, the closer to 0 it gets. All 5 of these get very, very close to 0. Constants don't change. So limit as x approaches infinity for these fractional things, you literally get 0 plus 0 minus 0 over 8 minus 0 minus 0. But this is just 0 over 8, which is 0. And in fact, if you know the rule in college algebra that if the degree of the bottom is bigger, the horizontal asymptote is y equals 0. Limits at infinity are basically like horizontal asymptotes. That's where if they level off, if there is no horizontal asymptote, they don't level off. If there is one, they level off, and that's what the limit at infinity is going to be. So if you knew that rule from college algebra, you could have known this answer was 0 without doing all that work. Okay, what about limits of piecewise functions? So if you have a piecewise function like this, I have a linear piece when x is less than 3. I have a constant when x is between 3 and 8. And then I have another linear piece when x is greater than 8. So notice there's only 2 breaks in the graph. There's a break at 3 and there's a break at 8. And that's the 2 limits they're asking about. Because what can happen with these piecewise functions is you can have 3 different pieces actually. You might have a line going like this, and then you might have a horizontal piece like so. And then you might have another one going like that. They can be disattached here and disattached there. Or sometimes they all connect up. Sometimes the closed circle lands right on top of the open circle and it closes it up. And then this open circle may or may not land on top of the closed one, but if it does, it can close it up and it can be fully connected together like this. And that affects the answers to f of 3 and f of 8. And it could affect the limit answers too, because the left-sided limit here can disagree with the right-sided limit, or maybe they do agree with each other. So really, all you have to worry about here is you can either try to graph this if you remember how to graph these in college algebra. That can take a while. Or just plug the 3 in. If I put a 3 in, because this is a polynomial, that's when you can just plug the 3 in. 3 minus 1 is 2. And this is saying the answer is always 2 for any number between 3 and 8. So if this is saying the left-sided limit is 2 and the right-sided limit's 2, they agree with each other, so the overall limit is 2. And that also means if you were graphing it, that the open circle would land on top of the closed circle and it would connect up to it. But at 8, the left-sided limit's going to be 2. The right-sided limit's going to be 8 plus 1, which is 9. Now they disagree with each other, so the limit does not exist, and it's also that it doesn't exist because it's not infinity or negative infinity. It's because the answers are disagreeing with each other. 2 and 9 aren't anywhere close to infinity or negative infinity. So it's not that this graph is shooting way off to infinity or negative infinity. That happens when you're close to an asymptote, actually. Or if you go way out to infinity or negative infinity for the x value. So that's where we do say the limit does not exist. So based on those 2 answers, I can tell that if I was graphing this, what would have happened is it would have been a open circle going to the left the closed circle would have landed on top of the open circle on the left side. But then on the right side, there would have been an open circle going somewhere separate from that closed circle. This is what the graph would have shown some way or another. Because if the limit exists, these pieces are going to connect up. When the limit doesn't exist, that usually happens when you have separate pieces like this. Because then your left-sided limit disagrees with your right-sided limit. Where here, the left-sided and right-sided limits agree with each other. So another time that the limit can be infinity is something like this number 15. Remember our log graph from last time? We actually did this last time. Remember how all logs go through 1, 0, which is why the log of 1 always equals 0. And then they also go through the base, comma 1. So natural log is log base e. So then 2.8 comma 1 is going to be another spot on this graph. Because if I do the exponential version, it'll be 1 comma 2.8. And then your other point will be here. So here's the log graph. And even though this looks like it flattens out, it actually keeps going up forever. So if you ever did a limit as x approaches infinity, for a natural log or any kind of log like this, that answer is going to be infinity because it's just going to keep going up and up and up forever. That's not what this problem's about, but this problem says, what's the limit as x approaches 0 from the right? So a one-sided limit can have an answer or not have an answer the same way a two-sided answer might not have a two-sided limit might not have an answer. And really, I can't do the left-sided limit here. The left-sided limit to this problem is going to automatically be does not exist because the log graph doesn't exist over there. There's literally nothing over here happening. Remember how logs can't equal negatives or 0? So I can't get close to 0 from the left. There's nothing to go up or down to touch because the graph doesn't exist there. So the left-sided limit doesn't exist, which means the overall limit is definitely not going to exist. But the right-sided limit might have an answer to it, actually, because there is something over here. But if I come in close to 0 from the right, it's going to shoot way down to negative infinity there. So this answer can be negative infinity, which is technically not an answer also, but they specify this more than just saying it doesn't exist. So when they want you to say does not exist, that's when they say does not exist, but it's also not infinity or negative infinity. If your limit answer is infinity or negative infinity, it technically also doesn't exist, but it's a more specific answer at least. It doesn't exist because it is negative infinity is what we're really saying. But it's different than a generic does not exist where you're getting disagreement on your answers. So where does the function have a vertical asymptote? Literally it has one at 0. And that's why whenever there's a vertical asymptote, then if you get close to a vertical asymptote on either side, that's when limits go shooting way up to infinity or down to negative infinity. And if you do like a generic vertical asymptote, not from this log graph, but from some other graph, remember our other vertical asymptotes we had? Where often you'd get a graph that would go like this, and then the other one would be maybe here. Let me do it this way this time. This can happen in a vertical asymptote graph. And then the left-sided limit is infinity. The right-sided limit is infinity. That can happen. So the limit as x approaches, let's just say this is a 5 here. 5 from the left, that can be infinity. And then the limit as x approaches 5 from the right, that can be infinity. So even though these things don't really exist, there's agreement between them, so then the overall limit can be infinity, since there's an agreement between those two. Or maybe one curve goes up and the other one goes down, and then you can have infinity for the left-sided limit and negative infinity for the right-sided limit, and then you would say does not exist for the overall limit, because there's disagreement then. And that would be the does not exist, and it's not infinity or negative infinity type of answer. Okay, here's one of these business problems, and it involves what we're doing in this section about limits. A company training program has determined that on average, a new employee produces PS items per day after S days of on-the-job training. Where, and you can't see that, but it says P of S equals 58S over S plus 7. So here's a good old rational function right here. Find and interpret the limit as S approaches infinity. So what we really want to do on number 16 is limit as S approaches infinity for a rational function that's 58S over S plus 7. So a couple ways of thinking about this problem. My degree, highest degree, is S to the first power. So what if I try the good old divide everything by the highest power, S? I can take each term and divide by S. This would cancel and give you 58. This would cancel and just be equal 1. And then when you plug infinity in, this plugging infinity in here will make that go to 0. So you'll get 58 over 1, which is 58. So doing the limit at infinity with the technique of dividing everything by the highest exponent, that gives you an answer of 58. Also, college algebra knowledge, the degree of the top is 1, degree of the bottom is 1. They have equal degrees. So that's when the horizontal asymptote is y equals the ratio of the leading coefficients, which is also 58 divided by 1. So this would have a horizontal asymptote of 58. So that would mean way out at infinity, the graph's going to level off at 58. Since it actually had a horizontal asymptote. So the limit exists, it's 58 because that's the horizontal asymptote, and or my algebra technique of dividing by S has helped. Okay, so the number of items a new employee produces gets closer and closer to 58. We're definitely going to put 58 in one of these 4 boxes. As the S, what's S about? S is the number of days on the job. And S is going to positive infinity, so it's getting larger and larger and larger. So the first answer is wrong because it says the number of days of training decreases. No, that's positive infinity is increasing. So the number of items that a new employee produces, see, that's what P of S is about. That's the Y value. The Y value is getting closer and closer to 58 as the number of days, which is the X value, increases forever. Now, nobody can work for an infinite number of days, but they're just saying as that gets larger and larger. So in other words, an expert at their job, the best they could do is make 58 of these things. There's just a limit to how much time in a day that you can make these things for. So that's 58. So there's 100% on section 3.1 homework, all 16 problems. And there's your first taste of actual calculus concepts, limits. Calculus was independently discovered or invented in the 1600s, about 400 years ago, and famously by Isaac Newton, who also created the laws of gravity or discovered those. And there was a German guy at the same time, supposedly, that invented calculus at the same time Newton did. And they actually were big rivals, and each one thought the other somehow stole their work from each other, and they never got along with each other. And each of the followers of them, because back in that day there wasn't a lot of contact over far distances. So Isaac Newton was in England, and this German guy, their followers didn't really talk to each other much. So each one had their own little notations, and the followers, people that followed them and produced new books down the line, there was slight differences in how they did certain things, and each one had some good things that they contributed. But the big breakthrough was this idea about limits. Limits really open things up. And it took us from like situations where our graph says there's no answer to suddenly getting answers. And it really opened up a whole new world because of that. It was a big breakthrough in math. Okay, so that was section 3.1. Next time we're going to do a little more with this in 3.2. Next time we're really going to also look at the function values. How do the function value answers, so far up to this point, we didn't really care how they were compared to all these answers. But when you get agreement between limit answers and function answers, that's a new concept that section 3.2 is going to cover. In 3.1, you don't really care if the function value even has an answer or if it agrees with the limit answer or not, but we will see that in the next section. So see you next time for section 3.2.